So this is node 1, node 2, node 3, node 4, node 5, node 6, node 7, and node 8. We can use this by taking a two-noded element. This is element 1, this is element 2, this is element 3, 4, 5, 6, 7. So element 1, element 2, element 3, element 4, element 5, 6, element 7, or we can as well as come up with the three-noded element from here to here, right? This would be element 1, this is element 2, and this would be yeah, so let me just remove this part of it. So let's make it only 7 noded, so this makes our life easier. So, and element 3 just been loaded by this. This has been loaded by load P. So we have three noded elements. Let us write connectivity table. I will define what is a connectivity table soon. And we have two noded elements connectivity table. The connectivity table is defined as a table that will define our elements, and an element is nothing but is formed by arranging the it is defined as element constitutes of nodes, and the boundaries of these nodes would give you your entire element. So let us try to write a table here. So let us write this table as, so this is element number node A and node B, because for a two-noded element we want to define this as node A and node B for a given element E. So for the first, if I look at my, if you look at here, if you look at here, your element 1 is made up of node 1 and node 2. So element 1 consists of node 1 and node 2, whereas element 2 consists of 2 and 3, and then element 3 constitutes of four consists of 4 and 5, and 5 consists of 5 and 6, and 6 constitutes of 6 and 7. So let me redo it. So just in case if you didn't, so the element 1 consists of node 1 and node 2. This consists of node 2 and node 3. This consists of 3 and 4. This consists of 4 and 5. This consists of 5 and 6. This consists of 6 and 7. So let us see again the same color matching. These are the nodes in brown color. The one A is 1, B is 2. For the element 4, A is 4 and B is A and 7, B is 7. That's what I have written as my connectivity table. So the entire structure is made up of 6 elements, 1, 2, 3, 4, 5, 6. But each element has a connective nodes for it. For this one, an element is defined by a set of nodes, and this set of nodes for a two-noded element is A and B. It defines our mesh or nothing but our geometrical discretization. So our entire structure of length L is divided into 6 elements of two-noded, and each element is having such a kind of connectivity table. For example, element 4 has a connectivity table with node A as 4 and node B as 5. Similarly, let's have a look at our three-noded element for the same thing. Node A, node B, and node C, and this is our element. How many elements are there? We have 1, 2, and 3. So let's have a look again. We have element 1, element 2, and element 3. Element 1, so anyway, let us draw it again. A three-noded element would be something like this, where we find this as node A, node B, and node C. So for that, our connectivity, so node A is 1, and node B is 3, and this is 2. Have a look at it again when I'm writing it. So this is node A, this is node B, and this is node C. Similarly, for the element 2, we will have this one as 3, this one as 5, and this one as 4. Similarly, for this, we will have this one as 5, this one as 7, and this one as 6. So for element number 2, this element, this if I see, A is this one, B is 5, and C is 4. So that's what I have written for 3, 5, and 4. This is our connectivity. And we have seen in the last time that the shape functions would be defined as in the corresponding cases. In this case, U tilde is nothing but A1, A0 plus A1x. This is nothing but UA, NA plus UB, NB. That is nothing but where NA of x is given by 1 minus x by LE. LE is not necessarily equals to L. L is the length of the bar. This is length of the bar. LE is, this fellow is length of the element. Let me see, I'm getting few. let's say in here, see here, this is the length of point for a 2 bar, whereas a 3-noded bar. So LE is different for each and every element. Okay, so you have to bear that in the mind. Okay, so similarly, for a 3-noded element, U tilde is given by A naught plus A1x plus A2x square. Now you need to understand that this is not a good way because A0, A1, A2 doesn't have a physical NA plus UB, NB plus UC, NC. And our NA is defined as X minus XB, X minus XC divided by XA minus XB and XA minus XC. In the rotation manner, you can also write your NB of X as X minus XA, X minus XC divided by XB minus XA into XB minus XC. Similarly, NC of X is defined as X minus XA divided by XC minus XA and XC minus XB. So this is how we have defined our this thing. And we have shown that in the previous class that no matter which element you see, partition of unity has to satisfy. Partition of unity means summation of I can be number of nodes. I is equals to 1 to number of nodes in a element is for evaluated at any x, no matter it is whatever is the x, has to be equals to 1. So that means in this case, NA of x plus NB of x is equals to 1 for 2-noded element. Similarly here for a 3-noded element, it is NA of x plus NB of x plus NC of x is equals to 1 because it is 3-noded element. So we have seen that the partition of unity or this property has a greater meaning. It says that even the lowest possible deformation mode can also be obtained. The lowest deformation mode is is rigid body motion. Okay, so strain. So and the choice of polynomial is also from lower to upper side because you want to capture first you want to capture rigid body displacement and second one would be constant strain. This has no strain. The rigid body displacement has no strain. Rigid body displacement is like if you take a pen and you are just moving it and every point on this is moving by the same amount. So that's the reason what happens is the displacement at any given node is same. That means no point has a relative displacement compared to the other that gives you no strain. The second one should be, it should be in the increasing order. It should be always in this and constant strain. So that means if I plug it at one point and then I displace it other, we have a relative displacement of one node compared to other that would give, or one end compared to the other end, that would give me a constant strain, and then you will have quadratic, linear, quadratic and higher order things. So if you have to go in a gradual, if you go in a gradual manner, then your convergence is also will be in a regular manner without any difficulties. I will talk about convergence and completeness at a later point of time, but at this point of thing, you have to see that you have to introduce these things in an increment, in a gradual manner, rather than targeting. So first is no strain, then linear strain, constant strain, then linear strain, quadratic, cube quadratic. You have to go in an increasing thing. That is always the best polynomial assumption. So your u tilde has a naught plus a1x plus a2x. A naught x to the power of 7 plus a naught, 10 plus a2x to the power of 15. This is not a good option because it will not give you in an increasing fashion. We want to introduce one after the other. So it's like even when you are studying in a high school, you'll go for first grade, second grade, third grade, and you don't directly jump from you go to second grade and then after directly you go to the sixth grade and then you learn so much enough that you'll go to the 10th class. So that would not be a better thing even in the approximation. It is always gradual to do it first grade, second grade, third grade, fourth grade. In the same manner, the strain has to be no strain, constant strain, linear strain, quadratic has to be introduced in a gradual fashion. And if such kind of things has been done in your polynomial assumption, then it will always give you a better convergence at a later point of time. At this thing, this is quite enough. And then let's go to the next topic. So now we have our element library for 1D. Now let's go for the 2D library. For 2D library, let us take a simple square domain or square or a rectangular domain. So if you have this kind of a domain, when I'm discretizing it, I can discretize in several different fashion. Let's say the first best method of the discretization would be something simpler discretization. I'm following it in this case. Okay, so knowingly or unknowingly, what I've created is a structured mesh with that your black color domain is discretized using this arbitrary brown lines to make elements. So this is element number 1, element number 2, element number 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Don't worry why I'm numbering it. We'll to come to that point in a short while. Similarly, I can discretize my nodes as these things. These are my nodes. These are nodes, and are elements. So, and elements are bounded by nodes in this manner. Now in this thing, the natural thing what you would see was this is what is called a quad element. This one is a quad element. The same kind of thing I could have discretized in a different manner. Let's see an alternate discretization. This is a discretization. There is no hard and fast rule how I have to discretize it. I could take the same rectangle. I'm poor at drawing the same rectangle, but assume it's the same rectangle. So I could discretize the thing in a different manner. Let me put it in this manner. So so now, if you look at it, these are the nodes. It's the same rectangle. I'm sorry for not drawing the similar thing, but assume it's the same configuration. Now I'm discretizing it in a different manner. So here again the same thing, these are, and my element is given by either this kind of a triangle or this kind of a triangle with nodes ending on it. So these are called triangular elements. Element, and this one, this fellow is triangular element. Just like a 2D and 3D, now I will try to develop for this a quad element and triangular element in a separate fashion. So from here onwards, let's see this one, quad element element. Let me see if I have any questions. So anyway, not a problem. So let's see. In a quad element, something like kind of a trapezoid. And however, in this, it is, I'm just drawing a standard triangle. It can be any kind of a triangle. I'm just drawing a standard triangle. So anyway, let me also draw it in a complete generic fashion so that you don't have any problem. So let me draw, this can be a quad element is something like this is a linear it is joined by 4 lines for the 4 nodes. This is a quad element, and a triangle element, generic triangle element would be something like, so that means a 2-dimensional domain can be discretized by either set of few triangles or by these kind of quads. So here let's understand how many nodes are there. 4 nodes are there. The nodes are, let me call it as A, B, C, D. It's a usual practice to either go in a clockwise, anti-clockwise manner or a clockwise manner. So generally I followed numbering scheme with an anti-clockwise manner. Similarly, I can use A, B, and C. So here I have 4 nodes. The 4 nodes are A, B, C, D. Here I have 3 nodes. They are A, B, and C. And I can see that the node A is defined by XA and YA, and node B is defined by XB, YB. Node C is defined by XC, YC. Because I have, it's a 2-dimensional. This is X, this is Y. So similarly, node D is defined by XD and YD. While here in this we have 3 nodes. A is defined by XA, YA, B is defined as, and C is defined as XC, YC. For some reason, let's say I'm solving a heat transfer problem, and the degree of freedom I'm looking here is a temperature field. So the same thing can be applied for a structural problem, but for simplicity, I am picking a temperature field. So let us say our degree of freedom is temperature, or our unknown is temperature. So that means we want to know if I know temperature at A, if I know the temperature at TB, if I know the temperature at EC, if I know the temperature at TD, what would be the temperature at this point or that point or any other point inside this element? That is what I want to write down. Similar temperature at TA, if I know the temperature at TB, if I know the temperature at TC, can I write the temperature field anywhere inside this domain omega, inside this omega for these things? So for that, let us see how many unknowns are, how many known values are there. We have, in this case, 4 knowns. Those knowns are TA, TB, TC, and TD, while here we have 3 known, that is TA, TB, and TC. Field inside this element at any, since it is 2-dimensional, let me write it. T is a function of X and Y. I want to write this as a function of Y. Now, how many unknowns I have? 3 knowns. So I can write it as A0 plus A1 X plus A2 Y plus write this fellow as T of X comma Y is equals to, since I know only 3, I can have a liberty of 3 constants, A0 plus A1X plus A1Y. Now again, I will ask you at this point of things, why I have written this form? Why not I write the same thing, T X comma Y, as something A0 X to the power of 7 plus A1 X to the power of 15 y to the power of 10 plus A2 y to the power of 25 plus A to the power of A3 x. Why not this choice? So this choice is again not a good choice. If you require, you can write such kind of things, but this choice is not good. This choice is not good. This choice is good. Why, we will come to know. Similarly, here also we can write this temperature field. This is an approximation. This temperature field is an approximation. We can write this approximation as y0 in the form of a0 x to the power of 5 plus y to the power of 5 a1 x x20 plus a2 x15 y7, or whichever form it is. This is also not good. This is good. Y. So let us so if you have given such kind of things, how to come up with the best possible polynomial? This is our polynomial approximation. We are making a polynomial approximation. To make such a polynomial approximation, I would request you to recollect something called your Pascal's triangle. Use Pascal's triangle. Okay, let me use Pascal's triangle. So let's write it as 1, this as x, this as y. So let's write it here as x square, this as xy, this as y square. This is x cube, x square y, xy square, and y cube. Similarly, I can keep on writing it x to the power of 4, x cube y, x square y square, x y cube. I mean, I can keep on writing this kind of a standard triangle. So now, how do one choose which coefficients to, which bases to use? So if it is a quad, I would say use these things. Let's say I'm using a quad. If it is a quad, use this is a good thing. So can you see it is the shape of a quad? So if you have, this is for a 4 noded. So 1, 2, 3, 4, 4 noded. If you need a 9 noded, I would suggest use all these terms. Use all these coefficients. This is one thing. If it is a triangle, I would suggest you to use something like this. This is for a 3 noded triangle, and this is for a 6 noded triangle. Let me tell you what I am talking. So if I have the same thing, this is 4 noded quad, 4 noded constant strain, or a linear quad. You can also call it as linear quad. This one is, let's say, if you have nodes such that the element is defined, we can have with the central element, or we don't have a central element, the things will change. So this is a special node. Let me put it in this manner. So if you don't have it, will become a serendipity element. So, but here let us say it's a 9 noded quad. 9 noded quad. So why 9? Because 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 noded. This is quad or quadratic quad. Okay. Similarly, you can also draw a triangle such that same triangle nodes like this, or one node here, one node here, one node here, and one mid node at every side. So here I have 3-noded triangle. Here I have 6-noded triangle. So here I have 3 unknowns. Here I have 6 unknowns. Here I have 4 unknowns. Here I have 9 unknowns. So no matter what I choose, I have to write my temperature field as a basis function times the coefficients. So in this case, this number of coefficients are 4. In this case, the number of coefficients are 3. In this case, it is 6. In this case, it is 9. But the choice, anyway, this will run to A naught through an, where n is equals to 9 here, n is equals to 4 here, n is equals to 3 here, n is equals to 6. There is no problem with A naught through an. But what is the choice of basis? This is important. What is the choice of basis I use it? Can I use y xy, or shall I use x to the power of 10, y2, x to the power of 15, y15, x to the 1, y to the power of 2, x4, y8. Is this good or is this good? So to do that, we'll go back and use our Pascal's triangle. So whatever, if it is a 4-noded quad, this is noded quad. This is for the 9-noded quad. Similarly, this is for a 3-noded triangle, and this is for a 6-noded. When you draw this triangle, whichever it is encompassing, take those things into your basis function. If you take those things into the basis function, automatically you will lead into a complete polynomial. So what is a complete polynomial? Like we have this advertisement, right? Raymond's the complete man, something like that. What does that mean by complete? Similarly, there is some meaning for the completeness in the approximation, which we'll come to know in a couple of minutes. But if you don't know how to pick a complete polynomial, the best thing, or it's like a template based method to do, is to follow this Pascal triangle and use whatever you see in this Pascal triangle. So if it's quad, you draw with an inclined thing, a square, the box. If it is a triangle, you just say on a horizontal basis, you keep drawing this triangle encompassing the number of nodes. So the complete thing suggests that for a 4-noded quad, for 4-noded quad, we have seen that the basis is 1, x, y, and xy. Similarly, for 9-noded quad, the best choice is 1, x, y, xy, x square, y square, and x square, y square. Is there no, I'm not done, sorry, it's still there. X, y, x square, y, and x square, y square. You can see 1, 2, 3, 4 here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So how did we choose? I just took all the coefficients within this thing. So 1 is there, x is there, y is there, xy is there, x square is there, y square is there, xy square is there, xy square there, x square, y square is there. That's what I have written in this thing. Similarly, if I take triangle, then my basis function is 1, x, and y. If it is 6 noded, I can clearly see that it is 1, x, y, x square, xy, and y square. So this is the choice of basis. So this is basis and this is coefficients. Okay, so let me see, I'm getting few questions, I guess. Please stop me. I'll be happy to answer this thing. They have chosen it, except few good books. So now let us write for a 4 noded quad. I write my temperature x comma y as a naught plus a1, because a naught into 1, a naught, a1 into x. This is x plus a2 into this y plus a3 into xy, or I can as well as write it as 1 x y xy multiplied by a naught, a1, a2, a3. It's the same statement. Similarly, for a 3 noded quad, I can write t x comma y is equals to a naught plus a1x plus a1y is equals to 1 x y a1 and a2. Similarly, for a 6 noded quad, not quad, triangle, we can write 1 x y x square xy y square into a naught, a1, a2, a3, a4, a5. So similarly, for a 9 noded quad, one can write y as a naught plus a1x plus, anyway, let me not write it expansion, I'll write it in a short form. It is written as 1 x y x square xy. You can pick any order, it doesn't matter, as long as all the constraints are there. So x y square x square y square and x square y, all the 9 things multiplied by a naught, a1, a2, a3, a4, a5, a6, a7, a8, these things. This will give you the temperature approximation. These are all approximations. So this would be written in this manner. Now, as I said earlier, it is better I can represent everything as in a simpler fashion because I know my basis is changing. The temperature field is represented by basis times coefficients. So let me write this basis as capital X and this guy as A as a base. So any temperature field or any degree of freedom can be written as basis times the coefficient, and the basis we are choosing based on the Pascal's triangle. Now I said earlier, maybe in the previous class, I don't want to write this one in this fashion. I want to always write my T tilde, for example, 4-noded quad. I want to write T tilde x comma y. I can as well as write it as a0 plus a1x plus a2y plus a3xy, but I don't like this style. I want to write it as ta na plus tb nb plus tc nc plus td nd. So what I have to do, if I substitute in this xa ya coordinates, this would be ta. If I substitute tb nb coordinates, this would be tb. If I substitute xc yc, I get tc. If I substitute in this xd yd, I'll get td. So let me use it. Similarly, it can be, this is true for any given any element. That's the reason this is very nice to deal with it. So let me generalize it. So let me write it as, if I substitute tc, this is td. If I substitute, this one is 1 xa ya, xa ya. Basis function is 1 x y and xy. Similarly, 1 xb yb, xb yb, 1 xc yc, xc yc, 1 xd yd, xd yd. This is nothing but my basis function x. This form is obtained by the basis function. For 4-noded element, I said my basis function x is, I can write this as my basis function 1 x y xy times coefficients a0, a1, a2, a3. But if I substitute this at xa, at this x at a, xa, ya, xa, this will be ta. Similarly, if I substitute, let me finish this equation. So this into this will give you ta. So this into this will give you tb. This into that gives you tc, and similarly, this equation into these coefficients will give me d vector, column vector, is equals to, let me call this as A matrix. A is defined through substitution of actual coordinates of the nodes in the basis function. This is your basis function times my coefficient vector. This I call it as coefficient vector. So, but I want to replace my A's and put it in terms of TA, TB, TC. So for that, what I will define it as A is equals to capital A inverse times my temperature at the given nodes. Then I know what is my, this is nothing but A0, A1, A2, A3. This is nothing but I'm writing it as A vector. This is simple form, is nothing but this is A. This fellow is nothing but entirely your capital A. This is the same. And this A is this one, this T is this one. So I'm getting this A in terms of TA, TB, TC as this manner. But I know that my temperature field is given by X times A. But what is A? A is A inverse of T. So this is nothing but capital X times A inverse of, I'm replacing this by this statement. But we know that this form is nothing but N times T, or also known as N1, NA, NB, NC, ND times TA, TB, TC, TD. So this is the same thing. So if I look at this statement and this statement, I can write that the T is again same as N times T. So you look at these two are same. These two are same. That means N has to be defined through this. So I can say that for my 2 or 3 dimensional things, the shape function is defined by the basis times the evaluation of the basis at the nodal point by its inverse. So A is nothing but X defined at all the nodes. For example, you see X for us is 1 X, Y, X into Y. A is nothing but the same thing evaluated at all the nodes A, B, C, and D. So your shape functions, this is nothing but your, as we studied in the previous things, these are shape functions. The shape functions is defined by basis vector, and A is basis vectors evaluated at all the nodes, but not you evaluate A at basis vector at all the nodes and take its inverse and multiply in this manner, you will automatically get your shape functions. So this is a simplest manner, and this is true for your any element. This is the generalized, this is generalized derivation for shape functions. This is true for anything, for 1D, 2D, 3D, all the things it is true. Okay, this is a generalized derivation. So this is by defining 2D, I also defined it for the 3D itself. Anyway, I'll show you how the 3D, the basis vector is different, but this is the simplest manner you can do it in this manner. Okay, so this is how you do it. For example, for 3D, for 4-noded, your X is defined as 1, X, Y, and XY. For 3-noded triangle, this is quad, X, you evaluation of X at all the things with an inverse, so it should be easier. Similarly, for the 9-noded, you already know what is X, and the choice of X is best suited if you follow the Pascal's triangle. Okay, so this you need to make sure you remember it. So anyway, this looks good that we have obtained in some fashion. How does this shape functions look like? Shape, how does So if you want to see these kind of things, then I would request every one of you to become a child. Okay, let's become a child and let's think, how does this shape functions look like? So let's start with a quad. So I'm still having some difficulties in drawing the pictures, but anyway, I'll try to do my best. So remember, when you were in childhood, you want to make your own tent, right? So when you want to make your own tent, you would take a blanket from your home, from your bed. So you take your bed sheet covers, your other three members of your friends to hold it at every corner, and you raise this blanket by a unit. Okay, the same thing as a kid we used to do that. So it would look something like this. You raise this by a unit distance and ask your friends to hold this one at 0 at all other points. The tent would take a shape something like this. This is all 0. This is also 0, right? This is like a tent. A pole has been erected by at node A. This is node B. Node you have derived in the generic fashion, or you might have derived in the other fashion, n of xa ya has to be 1, and n of a at xb and yb, when you evaluate, it has to be 0. N of a when evaluated at xc yc has to be 0. N of a evaluated at xt yd has to be 0. So it is 0 at this point, 0 at this point, 0 at this point, and it is 1 at only this point. So this is at NA, evaluated at A will give you 1 at all other nodal points only. So then you can easily write your N of X. What you would think this fellow would be. So the easiest method to write it is in this manner. So you take this you take this fellow again. Okay, so what is the equation of this line? So let the points are xa, ya, a, b, c, d, like this. So for simplicity, let's assume that these are horizontal. So, or let me normalize it. So let us say it is purely horizontal and vertical lines. So that means the y, this y is same as this y. So this line, let's say it is y is equals to ya, and this one is, if it is horizontal, this y is equals to yd, and this fellow, and you can I mean, this is the simplest derivation I'm doing. You can still write the equation of line with respect to 2 points and you can get it, but I'm giving in the simplest case. So, and what is the equation of this line? Because this is vertical in nature, this is x is equals to xb, and this fellow is x is equals to xa, because both the things have same x, these things have same x, these things have same y, these things have same y. I can write it in this fashion. So then I can write NA x comma y as, if this is the thing, you need to one. The equation of this line is y minus yd, and the equation of this line is x minus xb. Or you can write x is equals to xb is nothing but x minus xb is equals to 0. So the easiest manner you can write this is this one. But you know that this should also give you, when I evaluate at a's, it should give me 0 values. So that's the reason you evaluate it at ya minus yd, xa minus xd. This is for horizontal and vertical lines only. If it is inclined line, you can still write it for the similar thing. Changing this to the corresponding lines, you can get it. So anyway, this is the easiest manner when people will do it. So either this is like a shortcut trick methods, but this will help you to visualize that how the shape functions looks like. The shape functions looks like you give a unit degree of freedom at the corresponding shape function, and you keep the degrees of freedom at all other nodes to 0, and the evolved shape of the domain or the element will give you the shape of the shape functions. Okay, so and this is the easiest method to write your shape functions. If you don't like easiest method or shortcut method, I would always say that go back and evaluate your, your x function, you invert your a function, multiply together. This will always give you the correct answer. In here, you can make some quick errors while understanding the concept. So this is only a cheap trick to show you the visualization, but I would suggest, if you want to derive it rigorously, you follow this approach. In this approach close. The shape functions are again very similar to 1D shape functions. In 1D shape functions, we have seen that when you are drawing for a two-noded element, you give a unit displacement at here, and the other places it was 0 for two-noded. For three-noded, you have shown that it is 1 here and 0 at other two, 0, 0, and 1. Here this is 1 and 0. So this is for two-noded and three-noded 1D elements. This is for a 2D element. Similarly, for a triangle, if you have a triangle, you raise this by a unit distance and hold this one at 0, hold this at 0. The corresponding structure it forms, or the tent it forms, is the n of a for the three-noded element. The same thing you can derive it, and any given things you can exactly derive it using this standard derivation. This cheap tricks many book gives you is for a simpler understanding of the shape, or the how the shape functions looks like. But I would suggest you always go back and use that basis function and inversion at the all nodes as your standard way to derive your shape function. So in your shape function. So this is how your shape functions look like for the 2D. Now coming to the 3D. Let's finish this class by defining something for the 3D. So anyway, before doing let's summarize the 2D elements. 2D elements. So you can write, this is 4-noded quad. The 4-noded quad will be something like these things. As I said, these need not be horizontal and vertical. It will work for any inclined things. For simplicity, I have chosen like this. Next one is 9-noded. let me do first draw the nodes and then this is 9. And there is serendipity element, which is like again a similar kind of no central element, central node. So this is called this is your 8 noded quad, also known as serendipity element. It has its inherent advantages. We'll discuss it in the later class. Next, anyway, we will come to the other shapes. The other shapes would be like this is 3 noded triangle and 6 noded triangle. You can go for higher order elements in this, even on the higher order elements with different kind of styles, but these are most common in the things. These are the common things that you also find it in the commercial software for certain inherent advantages. But people who are doing spectral finite element, they will also use several higher order quads, like they can have 8 by 8 kind of a, that 64 noded quad can also be there, or can be 81 noded quad, can be higher or even lower kind of things. So this is not just limited, but these are the things that I have presented here is the most that you find it in. And we'll also describe why these elements are mostly prevalent in the commercial software, why not the other things, because they poses with certain different problems. So the 3D things are nothing but the brick element and that element. So I think most of you might have eaten samosa several times, I guess. So that element is nothing but kind of a samosa. So that means this is the base of the samosa, and let's say this is the height of it, and you connect all the things. So this is kind of a samosa. If you are not understanding it, let me redraw it. So this is the base of the samosa. And you put some node on the action. You connect these 3 things to the top. This is it's a 3-dimensional figure. It would be a little bit difficult for you guys to deal with it, to understand, or maybe I might have drawn it wrong. I should have drawn the base as a dotted line. Let me draw the base as a dotted line. This is the base as the dotted line. Then this point is not in this plane, but at a higher point, not on this plane, but on a higher plane. Then you join all these things to this point. It's like a pyramid. You can just think it as a kind of a pyramid. So this is your these are your 3 nodes on a plane. This is out of the plane, and then you are connecting all 3 things to the thing. This is your tet element. So how many nodes are there? A, B, C, D. 4 nodes are there. Similarly, if I come to the brick element, so this is like a brick, and at every vertex you have 1, 1, 2, 3, 4, 5, 6, 7, 8. So A, B, C, D, E, F, G, H. So this is your thing, but now you need to understand that you have 3 dimensions. What are the 3 dimensions? This is the plane of the paper. So this is X, this is Y, and this direction is Z. Similarly, let's say this is X direction, this is Y direction, which is in the plane, and out of the plane is in the Z direction. So from this plane to this, there is some height. So you have X, Y, and Z direction, all the 3 things that are present in this system. So now your basis function or temperature field should be a function of all the 3. So let's say temperature is our variable. Here the temperature is function of X, function of Y, and function of Z. Similarly, the temperature field is function of X, comma Y, comma Z. Now, let us assume, since some basis function X times the coefficients. How many coefficients are there in this case? Since 8 nodes are there. 8 nodes are there here. So it will run through A0 through A7. So I will choose 1 X, Y, X, Y, Y, Z. Sorry, 1 X, Y, Z. X, Y, Z, X, Y, Y, Z, ZX. 1, 2, 3, 4, 5, 6, 7. 7 and 8. Y, Z. So you can see that everything is linear. If X is a constant, then XY will become still linear in Y. ZX will become linear in Y, and YZ will also become linear in Y and linear in Z. So this is the best thing. It is very much similar to Pascal's triangle, but in a 3-dimensional you can obtain it. So just follow the rules of the Pascal's triangle in a 3-dimensional sense. You can pick your complete polynomial basis for a 3-noded element. Similarly, in here, pick 1 X, Y, and so that will be my A0, A1, A2, A3. Or the alternate way of writing it is A0 plus A1X plus A2Y plus A3Z. So at this point, let me see if I have anything. As basis function. In here, the capital X is a function of 1 small x, y, z, x, y, z, something like this. In here, it is something like this, times your n. And I use the similar thing which I have used in the previous thing, that tilde. I'm sorry about it. Yeah, this is true. So now I evaluate it at different places. Then I will get TA, TB, TC, something like that, which is at all the degrees of freedom. Then X is evaluated at all the places. Then this will become A, and this will become A. So again, A is given as A inverse T, and but can also be written as N plus, I will write it short form, I 1 to N. So here N is equals to 8. Here N is equals to 4. So Ni Ti, or that can be written as N's into T. So if I make use of this, if I take this and substitute here and then compare the things, again my N shape functions is given by X times A inverse. The derivation is no different. It's the same. I don't have to. Only thing that changes is how to choose your basis function. This basis function now is a function of X, Y, and Z. And the only thing I would suggest you to pay attention is how to choose a complete basis that will help you in a later sense. So this is what you will get it. There can be higher order elements also. File properties. The higher order elements can be like a 6-noded TET. I mean, it's just an extension of what we are learning. So let me again draw it. So this is your base of the samosa or a pyramid, and this is at a higher point. You join it. So, and on each line, earlier we have one node at each vertices, but on every line, if you put a midpoint, it's a midpoint. This line, there is a midpoint on this 4, 5, 6, 10. Similarly, you can come up with a 27-noded brick. That means that first you will have at every vertices, and then point of here, midpoint of this line, midpoint of this line, midpoint of this line, midpoint of that line, midpoint of this 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 line. So you see the 3, and midpoint of this here, midpoint of here, midpoint of here, midpoint on this face, midpoint on this face. So you can see that it is on any given plane you have 9, and you have such of the things which are 3 in things. So this is 27 noded brick is there. This would be like quadratic in nature, quadratic in X, Y, and Z. This is also quadratic, but it is in triangular fashion, whereas this 8-noded brick are kind of linear brick, and this is linear TET. So this is what is the element library which we made use in this thing. So I think here we will take shape this element stiffness matrix in the subsequent classes. So at this point of time, I will stop all of you and ask if there are any questions from the gallery.